let's do some more AP review. This is 2006 ABBC Free Response 4. It is a table problem, so guaranteed, before we even start, you're going to be asked to do two things. You're going to be asked to estimate the derivative of this quantity, so in this case, the derivative of v of t, which would be a of t, by using old school slope between two of these points. It's gonna happen. And then you're also going to be asked to approximate integration of v of t, which would be x of t or y of t or s of t or whatever it is, but the position, by doing some sort of area approximation, trapezoidal, MRAM, RRAM, LRAM. It's gonna happen. So when you see a table problem, take a deep breath and think, yo, I can do two of these parts without stressing. I'm gonna be asked to estimate a derivative using slope, and I'm gonna be asked to approximate an integral using area. If you know that going in, you can ace two parts of any table problem. All right, so let's dig in. Rocket A has a positive velocity v of t after being launched upward from an initial height of 0 feet at time t equals 0 seconds. The velocity of the rocket is recorded for selected values of t over the interval from 0 to 80 seconds, as shown in the table that you kind of can't entirely see because I cut off some of the other side. There you go. So anyway, you get the gist. So, cool, there it is. All right, so Part A, find the average acceleration. Oh, hey, look, we're going to be asked to find slope of this table. I totally knew it. Of rocket A over the window from 0 to 80 seconds. Indicate units of measure. So the average acceleration is just the rate of change of the velocity. So my part A, right, A of, so my average acceleration, right, so A of t is v prime of t. So if you want average acceleration, right, the average acceleration is just going to be v of 80 minus v of 0 over 80 minus 0, which is 49 minus 5 over an 80. So you're going to get 44 over 80 in feet per second squared, because your velocity was feet per second over another second, which is feet per second squared. That's great. If you want to leave it as 44 over 80, that's totally fine. If you want to make it an 11 over 20 in feet per second squared, that's also fine. But remember the standing AP rule that if you simplify that and do it wrong, it's on you, and you took a right answer and turned it into a wrong answer. All right, so again, be careful simplifying. Part B. Using the correct units, explain the meaning of the integral from 10 to 70 of v of t in terms of the rocket's flight using midpoint Riemann sum. Oh my gosh, it's like I'm a genius. With 3 subintervals of equal length to approximate the integral from 10 to 70 of v of t dt. Cool. So again, totally a thing that's going to happen in every table problem, right? So first we're asked to interpret the meaning of the integral from 10 to 70 of v of t dt, right? So we don't have a variable for the position, like they didn't give us one, right? But so because this is a rocket moving up and down, I'm going to go ahead and use y for position or h for height. It doesn't matter which one. So I'm going to go ahead and be like, hey, let's call h of t the height of the rocket, just for my own benefit. So this would essentially be the integral from 0 to 70 of h prime of t, because that's what the velocity would be, meaning this is h of 70, oh sorry, it wasn't 0 to 70, it was 10 to 70, h of 70 minus h of 10, meaning this is the rocket's height at 70 seconds minus the rocket's height at 10 seconds. So essentially what this is this is the distance, and I can say distance, not displacement, because the velocity never changed sign. So this thing is always moving up the entire time, right? It has a positive velocity the entire time. This thing's moving up the whole time. And they told us that the rocket is being launched upwards and it's moving upwards all the time. So this is the distance the rocket traveled, right? And then if we look at our units, it's in feet, right? So in feet from t equals 10 seconds to t equals 70 seconds. So here's the important stuff that you have to mention. You have to mention what it is, the distance the rocket traveled. You have to measure the unit in feet, and you have to mention the time interval provided. If you miss any of that, you're going to lose a point for the explanation. We were then asked to use an MRAM, right, midpoint Riemann sum, to do 0 to 70, right, this window, in, I believe, 3 equal subintervals. Yep, okay. So the trick with an MRAM is that we can only do MRAM because in each one of these intervals, so we're going to do the interval from 10 to 30, the midpoint is going to be this 20, 22. We're going to do 30 to 50, the midpoint is going to be this 40 and 35, and then we're going to do 50 to 70, and the midpoint is going to be the 60. The reason that that's the midpoint value is because they gave you a table where the distance between the 10 and the 30, midpoint between 10 and 30 should be 20, and it actually is a value on the table. If 20 hadn't been a value on this table, we would not have been able to do a midpoint Riemann sum. So, each one of the intervals is a width of 20 because it's 10 to 30, which is a width of 20, and 30 to 50, which is a width of 20, and then 50 to 70, which is a width of 20. And then we're going to use the y values of the midpoints, which would be the 22, the 35, and the 44. So my integral from 10 to 70 of v of t dt is going to be approximately the height, or the width, whichever way you want to think about it, of 40 minus 20 times the height of the first box, which is 22, plus the same width of 20 times the height of the next box, which is the midpoint y value of 35, and then again the 20 for the width, and then the midpoint y value is the 44, right? So that's what they want to see you do, and then it's a question 4, so you are going to have to gut it out and do some of the math. The nice thing is there is a GCF of 20, right? So you can go ahead and add 22 plus 35 plus 44, which isn't awful, right? So I'd end up with a 66. If that were a 34, it would be 100, so it should be a 101. So this is a 20 times a 101, which is 2020, and it's measured in feet. So the answer is it's approximately that. Cool. So in order to get credit for this, right, you needed to use these 3 values. That was one of the points. You had to do, you had to have an explanation for what this thing was, and you had to give a final answer with units, right? So those were your 3 points. All right, part C. So again, not trying to brag here, just trying to tell you that the more you can anticipate what's going to be on your AP, the better. Walking into this, I called part A and part B without having done the problem first. If you can start to get to the point where you feel comfortable about what will be expected of you on an AP question, you're going to naturally do better. If you walk into something feeling prepared and you can look at the question and think, wow, that's exactly what I thought would be on it, you're going to do better. Now, part C, who knows? We'll find out what part C is. But part A and B on a table problem are usually pretty predictable. Or maybe it's part A and C that are predictable and part B throws some kind of curveball. But either way, on a table problem, usually there's something predictable. Oh, hey, here we come, rocket B, which makes sense because why would they call it rocket A if there was only one rocket? They just call it a rocket. Part C. Rocket B is launched upwards with an acceleration of a of t equals a 3 over the square root of the quantity t plus 1 in feet per second per second. At time t equals 0, the initial height of the rocket is 0 feet and the initial velocity is 2 feet per second. Which of the 2 rockets is traveling fastest at t equals 80 seconds? Explain your answer. Okay, so traveling fastest would be the velocity, right? So here's what we know in part C. We know the velocity. I'm going to call this VA now because it's easier. We know VA of 80 seconds is 49 feet per second, right? That's on the table. We can see it. Great. Okay. We know enough information to find VB of 80 because so that's A, right? So we know the acceleration of rocket B, which I'm going to call A sub B because it's easier, is a 3 over the quantity squared of t plus 1, right? Well, that is the same as saying V prime of B. So if I use the first fundamental theorem of calculus, if I integrate V prime, not of B, VB prime, or however you want to say it, if I integrate V prime with respect to t from 0, which is a value I know V prime of 0 because they gave it to me, to 80, which is a value that I want V sub B of 80, right? If I integrate that, I'm going to get, using the first fundamental theorem of calculus, V sub B of 80, which is a quantity that I want because I want to compare which of these rockets is moving faster, minus V sub B of 0, which is a value that I know because they gave that to me in the setup for part C. So I'm able to integrate this thing, right? It's straight up U substitution. So for me personally, I prefer to do my work separately. So I'm going to integrate this 3 times a t plus 1 to the negative 1/2 dt. It is technically U sub, but since your U is just a t plus 1, it's the same as your du. So if you want to use U sub, you can. I'm going to up the power by 1, which would be to 1/2, right? And divide by the new power, which is the same as timesing by 2. So I'm going to get that this is 6 square root of t plus 1, evaluated from whatever my bounds are, right? So this is going to be a 6 square root of t plus 1, evaluated from 0 to 80 equals my v sub b of 80, which is what I want, minus my v sub b of 0, which I believe they told me was a initial velocity is 2 feet per second, I believe. Right. So if I plug this guy in, right, I get that this is 6 root 81 minus 6 root 1 equals the thing I want, minus a 2. So I get a 6 times 9, which is 54, minus a 6 plus a 2 is my v sub b of 20. So when I clean all of this nonsense up, I think I get 50, and it should be in feet per second, is my v sub b of 20. So, v sub b of 80. I don't know how I turned that to a 20 2 steps ago, my bad. Okay, so I get v sub b is a 50 feet per second, and I get v sub a is a 49 feet per second. So since 50 is bigger than 49, v sub b is greater than v sub a, so rocket B is moving faster at t equals 80 seconds. Cool? All right. Now the AP did it slightly differently, using the same basic values, right? So the important thing is to compare this v sub b to what I have as v sub a, or just v of, you could just call it v of 80. I called it v sub a of 80. You want to compare the two of them. You want to make sure you have the right units. Again, there are slightly different ways to do this. I believe the AP did this and put a plus c, and then used this initial condition to find c, and then plugged in to find v sub b of 80, also fine. Any number of ways to do that.